All right, folks, let's do some examples. Here's an example. This is a really easy one. We're going to start you off real light, then we're going to get a little deeper. The radius of a circle is increasing. So the rate that we got a circle, and the radius is getting larger and larger and larger. So that means the circle must be getting larger and larger and larger. Okay? So the circle is changing, the size of the circle is changing because the size of the radius is changing. The radius of a circle is increasing at the rate of 7 feet per second. There's a rate of change. We got a per. What is the rate of change in the circumference over time? So, step 1 says, identify all given rates of change. Well, what did they tell us? What did they tell us is changing, and what value did they give it us? Well, they said that the radius is increasing. That means it's positive. If it said decreasing, it would be negative. The radius is increasing at the rate of 7 feet per second, but radius increasing 7. Now, since it's radius, it's going to be dr dt. So dr dt is positive 7. That's all we need for step 1. We identified the given rate of change. If there was another one, if it said, and something else is decreasing at the rate of 2 something, we'd say the rate of change in that is negative 2. All right, so it says, so the next one says, identify the unknown rate of change. What are they asking us to identify? Which rate of change are they asking us to identify? Well, it says, what is the rate of change in the circumference? They're asking us to identify the rate of change in the circumference. Well, that's circumference is c, so that's going to be dc dt. So we want to identify dc dt. So we're given the rate of change in radius, and we want to know the rate of change in circumference. Then it says identify a formula that relates the variables in these rates. We've got circumference and radius. Is there a formula that relates circumference to radius? Yes, it's called the circumference formula. And circumference is equal to 2 pi r. So now we have a formula. Step 4, plug in values for unchanging variables. There's only 2 variables, and neither one of them is not changing. Find the derivative of the formula. So we need to ddt this and ddt this. If I ddt this, it becomes dc dt equals, the derivative of 2 pi r is 2 pi, and then I put a dr dt on there. So there's my derivative. Plug in all given and implied values. Well, there's only 2 variables. There's dc dt and dr dt. And look, they gave me dr dt. They said it's 7. So I'm going to plug in 7 for dr dt. So now I'll have dc dt is equal to 2 pi times 7. And then step 7, solve for the unknown rate of change. Well, the unknown rate of change is dc dt. So I need to solve for dc dt. And the way I'm going to solve is I'm just going to multiply 2 pi times 7. So dc dt is equal to 14 pi. 2 times 7 is 14 pi. Now, there's 2 ways to look at it. You can leave it as 14 pi and just write down 14 pi, or you may need to multiply 14 times pi. So if you have a calculator, you can type in 14 times pi and get, whoops, my calculator, you know what answer my calculator gave me? It said the answer to 14 times pi is 14 pi. Yes, I appreciate that. Now I'm going to get a different calculator, one that's not going to force me to get pi as an answer. I'm going to go 14 times pi is approximately equal to 43.9823. 9823. There are units for this rate of change, feet per second, because circumference is a distance. So it's going to be feet per second. Okay? There's our first example. Let's try another example. Okay, we have another example here. This one involves the radius of a circle, so we have another circle. We got the radius, and it also brings up the area of the circle. It says the radius of a circle is decreasing at the rate of 3 inches per minute. So let's stop for a minute. Let's write that down. That's step 1. Identify all given rates of change. Radius decreasing at 3. So that means if it's a radius, its dr dt is decreasing, so it's negative, and it's decreasing at 3 inches per minute. So dr dt is equal to -3. At what rate is the area of the circle changing? So now it's asking, what's the rate of change in area? So that's going to be the unknown rate of change, which is dA dt. So we want to know, what is dA dt? We don't know. That's the purpose of this problem, to find out. When the radius is 37 inches. Okay, well, we're going to come back for that information later when we plug in all given information. So now, step 3. Identify a formula that relates the variables in these rates. Is there a formula that relates the area of a circle to the radius of a circle? Yes, it's the area formula for a circle. And the area formula is A equals pi r squared. That's the area of a circle. It has an A in it and it has an R in it. A and R, related to each other. Plug in values for unchanging variables. Well, we only have 2 variables, area and radius, and they're both changing, so we're not going to plug in anything for the unchanging variables. Step 5, find the derivative of the formula. Okay, well, we're going to do the derivative of A with respect to t, so that's going to be dA dt. That's it, there's the derivative, equals. Now we're going to do the derivative of pi r squared. Well, I want you to pretend, instead of pi r squared, what is the derivative of 3x squared? Isn't the derivative of 3x squared 2 times 3, x, and then the power goes down to 1, right? So 2 times 3 times x to the first power. So this is going to be 2 times pi times r to the first power. So the derivative of pi r squared is 2 times pi times r to the first. And then we have to put a dr dt on there. So here's our entire derivative. dA dt is equal to 2 pi r dr dt. And we have 3 variables here. We have dA dt, we have radius, and we have dr dt, the rate of change in radius. So now for step 6, plug in all given and implied values. We'll get to implied values later. For now, we're just given information. We're told that the rate of change in radius is -3. We're also told what the radius is. Look, when the radius is 37 inches. So we're going to put a 37 in here for radius. So it's going to be dA dt is equal to 2 pi times 37 times dr dt is -3. Step 7, solve for the unknown rate of change. Well, dA dt is the unknown rate of change, and all I have to do is multiply these numbers together. So let me grab a calculator here. I'm going to go 2 times 37 times -3. That gives me -222. So dA dt is equal to -222 pi. Now, if I were to multiply this now by pi, that would give me -697.434, or 4336. 4336. Now, this is area, and so the units are not inches. We're not going to say inches per minute. We're going to say inches squared, or square inches per minute. And the reason we're going to say square inches per minute is because area is always a squared unit. Square feet, square inches, square kilometers, square millimeters, square meters, whatever it is. Okay? So it's always put in inch, or area is always in squared units. And so this is our final answer right here. Or you could write it as -222 pi inches squared per minute. Okay, and that is so what's happening to the area? Since the since the radius is decreasing, this negative means that the area is also decreasing. Okay? Let's try another example. All right, here's another example. We've got the area of a circle is increasing at the rate of 12 square centimeters per hour. So now we're given another circle, but this time instead of telling us that the radius is changing at a particular rate, we're being told that the area is changing. So it says identify all given rates of change. Well, our given rate of change is a rate of change in the area. The area of a circle is increasing, so it's positive, at the rate of 12 centimeters squared per hour. So that means the area, dA dt, the rate of change in area over time, is 12, positive 12. And then it says, at what rate is the radius changing? So it's now, this time, it's asking us to tell us how fast the radius is changing, the rate of change in the radius. So now the unknown rate of change is radius. So that's dr dt. We don't know what the rate of change is in the radius. We're going to find out. At what rate is the radius of the circle changing when what's it? When the radius is 19 centimeters long. Well, let's identify a formula that relates the variables. Is there a formula that relates area of a circle to radius of a circle? Yes, we just did the same one in the last example, the area of a circle. So area is equal to pi r squared. That relates the area of a circle to the radius of a circle. Plug in values for any unchanging variables. We don't have any unchanging variables in this problem. So we're going to skip step 4. Find the derivative of the formula. The derivative of this formula is going to be the same derivative that we just did in the last example because it's the same formula. The derivative of A is dA dt equals, the derivative of pi r squared is 2 pi r, and then we have to put on the conversion factor, dr dt. So we have 1, 2, 3 different variables. Step 6. Plug in all given or implied variables. In this problem, they're all given to us. But this time, instead of being given radius and rate of change in radius, we are given rate of change in area, 12. So we're going to put a 12 in for this. 12 equals 2 pi, and then radius, when the radius is 19 centimeters long. So we're going to put a 19 here, and then dr dt. Last step, solve for the unknown rate. We're solving for dr dt. Well, there's dr dt. We just got to do some algebra here. 19 times 2 is 38. Now, we could divide by 2 on both sides and simplify it, and that's fine if you want to, but I'll skip that for now. 2 times 19 is 38, so we have 12 is equal to 38 pi times dr dt. Last step, to solve for dr dt, we got to get rid of this 38 pi. So we're going to divide both sides by 38 pi. 38 pi on both sides. That's going to cancel the 38 pi on the left side. And now dr dt is equal to 12 over 38. So dr dt is equal to 12 over 38 pi. Now, your teacher, your professor, whoever may expect you to reduce this. In order to reduce this, you just divide the top and the bottom by 2, and you'll have 6 over 19 pi. You could also plug this into a calculator and get a value for 6 over 19 pi. So if we did that, 6 divided by 19 pi, that would give us 0.1005. So 0.1005. And what are we dealing in here? Centimeters and hours. So that would be centimeters per hour. And that would be the rate of change in the radius at that particular instant in time. Okay? Let's try another example, but let's move on to a different kind of shape. All right, here's an example. Now we're going to deal with a square. And squares have sides. Squares also have area, and squares also have perimeter. And all 3 of those things are related to one another. So this question says, the side of a square is decreasing at the rate of 13 millimeters per day. What is the rate of change in the perimeter of the square over time? And step 1 says, identify all given rates of change. Well, there's only one given rate of change in this problem. It says that the side, that's S. In case you didn't know, side of a square is S, and the perimeter is P. And now I want you to start thinking about how is the side of a square related to the perimeter of a square. The side of the square is decreasing. That means our rate of change is negative at the rate of 13. So side, that's S, ds dt. ds dt, it's always d dt, and then we just put whatever letter we're dealing, or variable we're dealing with here. ds dt is negative 13. It's negative because it's decreasing. It's 13 because we're told that it's decreasing at 13 millimeters per day. Then step 2 says identify the unknown rate of change. Well, it's asking what is the rate of change? What is the rate of change in the perimeter? Okay, so that would be, our variable is P. So that's d dt of P. That's dp dt. So we're trying to figure out what is dp dt. What is the rate of change in the perimeter? Identify a formula that relates the variables in these rates. There is a formula that relates the side of a square to the perimeter of a square. Perimeter means all the way around, the distance all the way around. Squares have 4 sides. 1 side, 2 sides, 3 sides, 4 sides. And if you add up the 4 sides, side plus side plus side plus side, that's S plus S plus S plus S. That's 4S. So the perimeter of a square is equal to 4S, 4 times the side length, because all the sides are the same, right? All right. We don't have any unchanging variables. The perimeter is changing, the sides are changing. And so now we just want the derivative. The derivative of P is just going to be dp dt. I hope you're recognizing a pattern here. The derivative of 4s is just 4, because it's a coefficient times a variable to the first power. 4x to the first power, the derivative of that is just 4. So the derivative of 4s is just 4. But because we are doing the derivative with respect to t, not s, we have to put on a ds dt. We have to put on a conversion factor. And so now here's our derivative. We only have 2 variables. We have dp dt right here, and we have ds dt. That's only 2 variables. So now for step 6, plug in all given and implied values. Well, the question told us that ds dt is equal to negative 13. So we're going to replace ds dt with negative 13. So now we have dp dt is equal to 4 times negative 13. And so the answer to that now is, so step 7, solve for the unknown rate of change, solve for dp dt. 4 times negative 13 is negative 52. And we're dealing in millimeters over days. So it's negative 52 millimeters per day. That is our rate of change in the perimeter. Okay? Let's try another example using a square, only this time let's move on to area. All right, folks, dealing with a square again, only this time it says the side of a square is increasing. So the square is getting larger. The side is getting larger, so the whole square is getting larger, right? If the square is getting larger, then the area of the square is getting larger. The side of the square is increasing at the rate of 5 meters per second. Let's stop there for a second. That's step 1. Identify all given rates of change. The side is changing it's increasing at 5. So that's ds dt, the rate of change in the side. ds dt is equal to, it's increasing, so that's positive 5. At what rate is the area of the square changing? So now we want to know the rate of change in the area of the square. That's A. So our unknown rate of change is dA dt. What is dA dt? That's what we're trying to find out in this problem. At what rate is the area of the square changing when the side is 43 meters? Okay, so the square is getting larger and larger, and the area is getting larger, and at some point that square is going to have a side that's 43 meters long. That's a big square, right? It's probably outside. All right. We want to know what is the rate of change in the area at that particular instant. Okay, so we need a formula that relates the area of a square to the side of a square. Well, that's the formula for the area of a square, which is area equals side squared. That's the formula for the area of a square. And it's relating the side of a square to the area of a square. Plug in for unchanging variables. I promise you we're going to have an example with at least one of those. Okay, but for now, both area and side are changing, so we're not going to use step 4. Find the derivative of the formula with respect to t. The derivative of a is dA dt. The derivative of s squared, if this was x squared, the derivative would be 2x. But it's s squared, so the derivative is 2s. But because we're doing the derivative with respect to t, we have to put our conversion factor on, ds dt. There we go. So our derivative is dA dt is equal to 2s times ds dt. We have 1, 2, 3 different variables. So to solve for one variable, we need values for 2 of the variables. Step 6, plug in all given and implied values. Well, we had 2 values given to us. We were told that ds dt is 5, so this is 5, and the question says when the side is 43 meters. So s is 43. So dA dt is going to be 2 times 43 times 5. Grab a calculator for this. You probably don't need one, but I'm going to do it anyway because I don't make a mistake on video. 2 times, although I do that all the time too. 2 times 43 times 5 is 430. So our rate of change, dA dt, the rate of change in the area is 430. Now we need units. We're dealing in meters and we're dealing in seconds. But we're also dealing in area. So instead of meters, it's meters squared, square meters per second, because area is changing. And that is the answer to this question. Okay? Let's move on to a different shape. Maybe something three-dimensional, right? Let's try a sphere. All right, here's an example with a sphere. You know what a sphere is, right? It's a ball, right? Okay? So, the radius of a sphere. Now, you may not, I don't know how well you understand spheres, but spheres are circular like a basketball or something, and the center of the sphere is in the middle of it. It's three-dimensional, and the center is in the middle, and the distance from the middle of the ball to the edge of the ball, that's the radius of the sphere. The radius of a sphere is increasing. That means the sphere is getting larger. If the radius is getting larger, the ball is blowing up. The radius of a sphere is increasing at the rate of 2 inches per hour. So the ball is getting larger, a little bit slowly, but it's probably eventually going to pop maybe. 2 inches per hour. So that is a given rate of change. The radius increasing at 2 inches per hour. So that means that dr dt is equal to positive 2, increasing at 2. At what rate is the surface area? You may have to look that one up on the internet. You may need to look up the formula for the surface area of a sphere, because that's what we're dealing in here. Okay? At what rate is the surface area of the sphere changing when the radius is 21 inches? So, our unknown rate of change is the rate of change in the surface area of the sphere. Let's just call that, if you want to call it SA, that's fine, but I'm going to call it A. All right, so dA dt is, we don't know, we want to find out. Identify a formula that relates the variables in these rates. We need a formula that relates the radius to the surface area of a sphere. Like I said, you may have to look that up. I happen to know the formula for the surface area of a sphere. The surface area of a sphere is equal to 4 pi r squared. 4 pi r squared. Okay? It's basically the area of a circle, only it has a 4 in the front of it, okay? So it's 4 pi r squared. Now, and its area, its surface area, so it's r squared. All areas are squared. All distances are to the first power, and all volumes are to the third power. Okay? You might say, well, this is a volume, Mr. Ryan. Why is this not to the third power? Because it's not the volume of the sphere we're dealing with. We're dealing with the surface area, the area on the outside of the sphere. So it's area, second power. Step 4, plug in values for unchanging variables. Well, we only have 2 variables, a and r. They're both changing. Find the derivative of the formula. Okay, this term, we're going to ddt this term, then we're going to ddt this term. If we ddt this term, we just get dA dt like we always do. dA dt is equal to. Now, what's the derivative of 4 pi r squared? Well, remember, we have to take our exponent and multiply it by the coefficient. What's 2 times 4? That's 8. So it's 8, then there's a pi, and then r, and our power goes down by 1. Our power goes from 2 down to 1, r to the first power. So r to the first power. Then we have to put on our conversion factor, dr dt. And there's our derivative of the surface area formula. And now we have 1, 2, 3 variables. So for step 6, in order to solve for step 7, we need to plug in 2 values out of our three variables. Well, we're given dr dt, which is 2. So we're going to put that here. And then the question says when the radius is 21, when r equals 21. So we're going to put a 21 right in there and then solve. So the rate of change, dA dt, the rate of change in the surface area of the sphere is equal to 8 pi times radius, in this case, which is 21, times the rate of change in the radius, which in this case is 2. And now if we just multiply all these numbers, we'll have 21 times 2, that's 42. 42 times 8, that's 320, 16, 336. You know what? I know, I'm on video. It's going to drive me crazy if I get it wrong. 8 times 21 times 2, and that's, 336. I was right. So dA dt is equal to 336 pi. And we're dealing in inches, and we're dealing in hours. So that's inches, but not inches. It's square inches because it's area. So square inches per hour. And you may need to, depending on whether you're plugging it into a computer or writing it down on paper or choosing an answer on a multiple choice, 336 pi is the same thing as 1,055.5751. 0.5751 square inches per hour, okay? And that's the answer to this particular problem. Let's do one more sphere problem. Let's do one where we have to calculate the rate of change in volume. All right, check this one out here. We've got the radius of a sphere again. The radius of a sphere is decreasing at the rate of 15 feet per minute. At what rate is the volume of the sphere changing? So now this question is still asking about a sphere. We're still dealing with a radius changing, but instead of asking about the surface area of the sphere, it's asking about the volume of the sphere. So we're going to have a completely different formula for this one. Well, it's actually not completely different, but it's a different formula. All right, so the radius of the sphere is decreasing. Radius, decreasing, 15 feet per minute. So we need a rate of change. We need a derivative. dr dt, because it's the radius. So dr dt, the radius is changing over time, decreasing at 15 feet per minute. So the rate of change is negative. So that's negative 15. And now it's saying at what rate is the volume changing? That's v. So our unknown rate of change is the rate of change in the volume. So that would be dv dt. So we want to know what dv dt is. That's what we're trying to figure out. Now we're going to identify some mathematical formula that relates radius to volume of a sphere. Well, the formula for the volume of a sphere actually includes radius. So we're going to use that formula. And the formula for the volume of a sphere, you could pause the video and go look up the formula, or you can just wait for me to write it on the board right now. The volume of a sphere is equal to 4/3 pi r cubed. See, it's a volume, therefore it's a cubed, the variable is cubed. Okay, the dimension is cubed. Third dimension, volume is a three-dimensional characteristic, quality. Okay? All right, so now, plug in values for unchanging variables. Well, there's only two variables, volume and radius. And both of them are changing. So we're not going to do step 4. Step 5, find the derivative of the formula. We need to ddt this and this. Well, the derivative of v is dv dt equals. Now, 4/3 pi r cubed. Here's what I want to do. I want to change the r temporarily just so that you can understand how this derivative works. I'm going to change the r to an x, and I'm going to get rid of the pi to make it a little bit easier. Okay? So what if we had 4/3 x to the third? What would the derivative of this be? Well, we know we're supposed to take the exponent and multiply it by the coefficient. Well, what is 3 times 4/3? Well, 3 times 4/3, we could either do 3 times 4, because this is the same thing as 3 over 1. 3 times 4 is 12 over 1 times 3, that's 3, and 12 divided by 3 is 4. Or we could just cancel the denominator. See this? When you multiply 3 times 4 over 3, we can cancel the denominator, and all we have left is 4. So the derivative of 4/3 x to the third is 4x, and then reduce the power by 1 from 3 down to 2. It's 4x squared. Now imagine that there is a pi in there. Now we're going to squeeze a pi in there, and it's 4 pi x squared. And now let's imagine the x isn't an x anymore, it's an r. So it'd be 4 pi r squared. 4 pi r squared. Oh, that sounds really familiar. 4 pi r squared. I've seen that before. So the derivative here is 3 times 4/3 is 4 pi r to the third. Power goes down by 1, so r squared. Does this look familiar to you? We'll get to it in just a second. But look, because we did the derivative of r and we're ddting, we have to put on our conversion factor, dr dt. But look, 4 pi r squared. Didn't we just see that as the formula for the surface area of a sphere? So the formula, or the surface area of a sphere, is actually the same thing as the rate of change in the volume of a sphere when you multiply it by the rate of change in the radius. So that's kind of cool. All right, so here's what we have. We have one variable, dv dt, a second variable, radius, and a third variable, the rate of change in radius. Two of these are given to us. dr dt is negative 15, so we're going to put a negative 15 in here. And the question says, at what rate is the volume of the sphere changing when the radius is equal to 70? So that means the radius here is 70. So that's a big number. We're going to square that number, so we probably use a calculator. So dv dt, so that's step 6, plug in all given and implied values. Now step 7, solve for the unknown rate of change. dv dt is 4 pi, and then 70, the radius, squared, times dr dt is negative 15. We're going to have to do this in the calculator. I'm going to do 4 times 70 squared times negative 15. 4 times 70 squared times negative 15. Negative 294,000. So the volume, dv dt, is equal to negative 294,000 pi, because we didn't even multiply the pi yet. And because dv dt is negative, that means the volume is decreasing. And it makes sense that the volume is decreasing because the radius is decreasing. Okay? And we don't have our units. It's feet per minute, but because it's a volume, it's going to be cubic feet. It's feet cubed per minute. There we go. And so that's our rate of change. Now you could do the negative 294,000 and multiply it by pi, and that gives you negative 923,628.2402 cubic feet per minute. That's pretty fast. A lot of volume, right? Okay. All right, so here's a situation with a volume and a radius. What I'd like to do now is I'd like to move on to a new shape. We're going to move on to right triangles. We're just going to do maybe 2 or 3 examples with right triangles, and then you should have a very solid understanding of the basics of related rates. All right, this is a really good example. We're really kind of getting into things that can be more practically applied. Now we're going to do the rates of change in the legs and the hypotenuse of a right triangle. And these are really pretty popular because oftentimes what you're dealing in is things that are moving away from a solid or from a stationary object, and the rates at which those two objects are getting closer to each other or farther away from each other. Okay, so what we're about to do right here is very closely related to a practical application of related rates. All right, so here's what we have. We have a right triangle. It says the hypotenuse of a right triangle. In fact, to make this easier to understand, let me draw a right triangle. Here's a right triangle. Okay, there we go. And it says the hypotenuse of a right triangle, that's this, is 26 feet. All right, so that means that the hypotenuse is not changing. The hypotenuse is constant, which means that if anything is changing, it's the legs of the right triangle. It says the hypotenuse of a right triangle is 26 feet. If one leg of the right triangle is increasing at the rate of 8 feet per second, then at what rate is the second leg changing when it is 24 feet long? All right, so I know this is a little bit different than the last several examples that we've done, so we're going to wrap our minds around this. Okay, we're dealing with the hypotenuse of a right triangle, one leg of that same right triangle, and the second leg of that right triangle. And we're dealing with how long they are. So we have the hypotenuse, which is often referred to as C. We have one of the legs, which may be referred to as A, and we have the other leg, which may be referred to as B. Commonly in a right triangle, when we're talking about the lengths of the sides, we often refer to them as A, B, and C. So now, part 1, the first step says identify all given rates of change. Well, it says that one of the legs of the right triangle is increasing. One of the legs is increasing at the rate of 8 feet per second. So we can either pick A or B as the leg that is increasing. Let's use A. Okay, so A, this leg is increasing. It's getting longer at the rate of 8 feet per second. That's a rate of change. That's a ddt. And it's the length of leg A, so that's dA dt. So we're going to say that dA dt is equal to 8 because it's increasing, that's positive, at the rate of 8 feet per second. So dA dt is 8. Then it says, at what rate is the second leg changing? Well, that's right here. That's the unknown rate of change. The second leg is B, and we want to know the rate at which B is changing over time. That's dB dt. That's the rate at which B is changing over time. So we want to know what is dB dt. We know what dA dt is. We want to know what dB dt is. Now we need to identify a formula that relates the variables in these rates. So we have a right triangle with 3 lengths, 2 legs, and a hypotenuse. Is there a formula in the world of math for right triangles that relates the 3 sides of the right triangle, that relates the length of the hypotenuse to the lengths of the 2 sides? Hopefully by now you have thought in your head, yes, Mr. Ryan, the Pythagorean theorem. So that's what we're going to use, the Pythagorean theorem. The Pythagorean theorem, a squared plus b squared equals c squared, right? And it relates a to b. Now you may say, yeah, but Mr. Ryan, it also has a c in it. That's okay. It's okay to have a formula that has an extra variable. That's just fine, especially if that extra variable is not changing. Step 4, plug in values for unchanging variables. A is changing, B is changing, but C is not changing. So we finally get to use step 4. We're going to plug 26 in for C because the hypotenuse of the right triangle is 26 feet and not changing. So our new formula now is A squared plus B squared equals 26 squared. And if you want to, you can go ahead and square 26. So let's see, I probably should know this one, but 26 squared is 676. So instead, we're going to say A squared plus B squared is equal to 676. And now you're about to see why step 4 is so important. Because what is the rate of change? When we do the derivative in step 5, find the derivative of the formula. What is the derivative of a constant? What is the derivative of something that's not changing? If something's not changing, its rate of change is 0. And so the rate of change in a constant, we've already learned, is 0. And so when we do the derivative of this, what's the derivative going to equal? What's the derivative of 676? The derivative is 0. And that's going to help us because having a 0 here instead of a 2c dc dt is going to make the problem a lot easier to solve. So this is why it's so important to plug in values for unchanging variables. Okay? So now we're going to do our derivative. What's the derivative of a squared? It's 2a, but it's not t, so we got to throw on the conversion factor dA dt plus the derivative of b squared is 2b or not 2b. All right, that's not as funny when I don't have students in the classroom, but maybe you laughed at it. Who knows? All right, 2b and then the conversion factor dB dt equals, and then the derivative of 676 is 0. And so here is our derivative. And now I want you to notice we have 4 variables. We have a, we have dA dt, we have b, and we have dB dt. So now we're going to do step 6, plug in all given and implied values. So now this is the first problem where we're going to have an implied value. Well, what are the given values? We're given dA dt, right? If one leg of the right triangle is increasing at the rate of 8, we're going to put that in for dA dt. So we would put an 8 here. And then it says, then at what rate is the second leg changing? That's dB dt. We're solving for dB dt. So now we have to plug in for A and for B. It says, at what rate is the second leg changing when it is 24 feet long? That's B. B is 24, right? So we're going to put a 24 in here. But we don't have the value for A. They didn't give us the value for A. So how are we going to find the value for A? Well, we have the Pythagorean theorem, right? We can find, if we have in the Pythagorean theorem, if we know what C is, 26, and if we know what B is, 24, then we can find the value of A. So let's do that maybe over here. A squared plus 24 squared is equal to 26 squared, right? Well, we already said that 26 squared is 676. 24 squared is 576. So A squared plus 576 is equal to 676. And if we subtract 576 here and here, we get A squared is equal to 100. And then the square root of both sides, and we get A is equal to 10. So now we can plug 10 in for A. So now for step 6, we have 2 times 10. dA dt is 8 plus 2. B is 24 times dB dt is equal to 0. And now here's what I'm going to do, is I'm going to subtract 2 times 10 times 8, that's 160. So I'm going to subtract 160 from both sides. 2 times 24, that's 48. So I have 48 dB dt is equal to negative 160. Last step, step 7, solve for the unknown rate of change. Divide by 48 on both sides. And we get dB dt is equal to, I should know this one too, but I'm going to use the calculator. Negative 160 divided by 48 is, let's see here, negative 10 over 3. Yeah, divide by, oh yeah, 16 goes into both of these. So negative 10 over 3, which is approximately equal to negative 3.3333. And this is a length, and we're dealing in feet per second. So we're going to say feet per second. Also, note that this rate of change is negative. That means that the length of B is decreasing. As A gets longer, B gets shorter. And that makes sense because this hypotenuse has to stay the same length. Okay? So there's an example of a problem that uses a right triangle. Let's do one more right triangle problem, and then I think you'll have a pretty good feel for this whole thing. All right, folks, last example here. Now this one's kind of a doozy, okay? Let's read through it real careful. One leg of a right triangle. Okay, so we've got a right triangle again. One leg, let's call it A. See, we have A, B, and C, right? One leg of a right triangle is increasing at the rate of 9 centimeters per second. Okay, so let's call that leg A. Increasing, so that's positive. So dA dt, increasing at 9 centimeters, so 9. And the other leg is decreasing at the rate of 7 centimeters per second. We've got two rates of change that are given to us in this problem, not just one. We're given two rates of change. Look at step 1. Identify all given rates of change. You might be given more than one rate of change in a problem. All right, so we've got to write both of them down. So the other leg is decreasing. That means it's negative at the rate of 7 centimeters per second. Well, what's the other leg? If the first leg is A, the other leg is B. So that means that dB dt is decreasing, that's negative 7 centimeters per second. So dA dt is not positive 9, and dB dt is negative 7. Well, if they gave us two rates of change, well then what could the unknown rate of change possibly be? Well, let's finish reading the question. At what rate is the hypotenuse changing? So in this case, all three sides of the triangle are changing. The legs, one leg is getting longer, one leg's getting shorter. That means the hypotenuse, and then in this particular case, the hypotenuse is also changing. So, at what rate is the hypotenuse changing? Well, the hypotenuse is letter C. So that would be dC dt. Not to be confused with circumference. In this case, it's not circumference. In this case, it's the letter C representing the hypotenuse. At what rate is the hypotenuse changing when the first leg is 52 centimeters and the second leg is 39 centimeters? They gave us lengths for two legs, which means we can use that information to find the length of the hypotenuse, right? By using the Pythagorean theorem. So let's go ahead and set up the Pythagorean theorem. Identify a formula that relates the variables in these rates. We're relating A and B and C. That's the Pythagorean theorem. A squared plus B squared equals C squared, right? And so, step 4, plug in values for unchanging variables. Well, in this case, all three sides of the triangle are changing, so we're not going to plug anything in. Step 5, find the derivative of the formula. All right, well, the derivative of A squared is 2A, and then we got to put on dA dt, right? The conversion factor, plus B squared becomes 2B dB dt. I know you wanted me to make the joke. Some of you did, but I didn't. It's okay. Some of you are happy I didn't make the joke. Equals, the derivative of C squared is 2C. That's a 2. dC dt. I'm kind of running into, so here's my derivative right here. There's my derivative. And I have 1, 2, 3, 4, 5, 6 variables, 3 lengths and 3 rates of change. And I need to plug in for 5 of them. If I'm going to solve for 1, I need to plug in for 5 of them. So they gave me dA dt, which is 9. They gave me dB dt, which is -7. They also gave me the length of the first leg, A, which is 52. And they gave me the length of the second leg, which is 39. I'm solving for dC dt, so I need to know what is the length of C. What's the length of the hypotenuse? Well, I can use the Pythagorean theorem for that. 52 squared plus 39 squared. So 52 squared plus 39 squared is equal to C squared. So really it's going to be the square root of the sum of those 2 squares. So let's grab a calculator. And we'll do the square root of 52 squared plus 39 squared. And that gives me 65. So C is 65. So I'm going to put a 65 in here. So let's go ahead and load everything up. We've got a 2 times A, the length of A, which is 52, times the rate of change in A, which is 9, plus 2 times B, the length of B, which is 39. Remember, these lengths are only happening at one instant in time, but this is the instant we took a picture. We took a picture of the right triangle. One leg was getting longer, the other leg was getting shorter, and then we took a picture of it while it was changing, and now it's frozen with the derivative. Okay? In this particular instant, in this particular moment, the rate of change in B is -7 is equal to 2 times C. In this moment, C is 65, and then we're solving for dC dt. Let's do a bunch of math. 2 times 52 times 9 is 936 plus, actually it's going to be minus, so we've got that -7 right there. 2 times 39 times -7 is minus 546 is equal to 2 times 65, that's 130 dC dt. 936 minus 546 is 390 is equal to 130 dC dt. This is positive because 936 minus 546 is positive, which means when we divide by 130 right here, it's going to be a positive number. That means the hypotenuse is growing. So if we divide by 130 on both sides, and we get dC dt is equal to 3. 3 centimeters per second, because it's a distance, so it's centimeters per second. That is our final answer. Okay? And that's how we solve a problem where everything's changing at the same time. We've got to have plenty of information, and we have to find some of that information. So these are all your examples for related rates. These are actually, I hate to say, these are actually the easy questions. What we're going to do in the next class is we're going to go on to the more difficult questions. We're going to do word problems where you have weird situations, like real life situations, and you have to try and create the shape, then do these 7 steps, and you'll always be able to get the answer, okay? But that's it for now, and good luck.